All right. Sorry, it took me a little while to get in here and get set up today. Uh, we have today is about covering the last of chapter 4, a little bit of chapter 5, and talking about the final, right? So, first of all, um, there was an email from a student who pointed out to me that in the solutions for exam 2, I forgot to include the page for 10B. Who did that? Who sent me that? You sent that? Okay. I put it out there this morning. So, and then what else? That was it. So 10B is now out there in the solutions. Also, I think there was a request to do a couple of problems. So I don't mind starting off by taking a look at some problems. Which one was it that you wanted me to look at? Number 15. Can I borrow a book real quick just to see that? Thank you. It was in 4.5. Let me look and see how long this problem is first. Number 15. Oh, okay. And then what was the other one? 15 and what? 25? I like 25. How about 25? So I'll read it and I'll give you the book back and so you can see it. It says, everyone have 25 or someone have a book? Everyone have a book at their table so y'all can look at it? Yes? Lies, do you mind sharing? Okay. All right. A Norman window has the shape of a rectangle surmounted by a semicircle. Thus, the diameter of the semicircle is equal to the width of the rectangle. Does everyone kind of understand what that would look like? Like this. Sorry, page 239, number 25. Mm-hmm. So it's a rectangle with a semicircle on top. That's called a Norman window. If the perimeter of the window is 30 feet, so I'm going to just jot this down. The perimeter of the window is 30 feet. Find the dimensions of the window so that the greatest possible amount of light is admitted. So that's it. That's the question. Here, you want your book back? Now, hang on to it? Okay, thank you. All right, so this is an optimization problem. And basically the steps are to try and come up with your objective function, right? What is it that you're trying to optimize? So what do we want to optimize? Sorry, I didn't hear you. Optimize the area of the window. Because the larger the area, the more light will come through, right? So we want to optimize the area. So that means I need a formula for the area of this window. So that's right. We're going to need to somehow combine the formula for a circle with the formula for the area of a rectangle. So I'm going to come up here, back up to my Norman window. I'm going to start to label some things. I don't know what I'll call height of the window is, right? I don't know how high it is. No one tells me that in the problem. From the bottom to where the semicircle is. So the height of the rectangle. The width would be from here to here. I don't know those, do I? Now, but what I can say is that the area of the green, right? This green in here, that area would be what? H times W. So that area right here would be H times W. Now, the area of the semicircle we can talk about. It's what? Pi r squared is the area of a circle, right? But it's half a circle, right? So how about half pi r squared However, we actually know something about r, don't we? It's half w. Isn't the radius half of w? Because w is the diameter of the circle, so half w is the radius. So using the fact that 1/2 w, 1/2 w equals r, what I can say here is that this formula would be 1/2 pi times 1/2 w squared. Now, the reason for this, the reason why I'm trying to get it in terms of w, is because I want as few variables as possible, don't I? Do y'all know what I mean by that or not? Okay, so this will be 1/2 pi times 1/4 w squared, which is 1/8 pi w squared. What the hell? What? I don't remember ever trying ExpressZip. Okay, so now let me go up and label this area up here in the yellow. It's 1/8 pi w squared. So the area of my window now, I'm going to come back over here where I had the question mark, would be height times width, so hw, plus 1/8 pi w squared. Now that is a legitimate objective equation, but I would like that to be in terms of one variable, right? So that I can use all the calculus and try and find the max min and all that stuff. So how am I going to eliminate one of those variables? Yeah, we're going to have to find a relationship between w and h using something I haven't used yet. What have I not used in this problem? That the perimeter has to be 30, right? So let's talk about perimeter. So this is what we called, remember what we called this? The constraint. The constraint on this problem is that my perimeter must be 30. But the perimeter, so if you were to start at one point, let's say I'll do it in this purple highlight. If I start at that top kind of corner there and walk around this window, I would have to go H, then W, then H, and then across a half circle, right? Wouldn't I? So let's add that up. It would be H plus W plus H again plus half of the circumference of the circle. I'm just going to use C. Is that all right for the circumference? But what is the circumference of a circle? But circumference is equal to 2 pi times the radius, or pi times the diameter, right? Right, 2 pi r is the circumference, but what is 2r? The diameter. So both formulas are valid. The reason why I'm using pi d is because don't I know what d is? The diameter is w, isn't it? So pi w. So c is actually pi w. So that means my constraint equation becomes 2h plus w plus 1/2 pi w equals 30. Agree with that? Can we solve that equation for h or w? Can you get h by itself or w by itself on that equation? Yeah? Which one would you prefer to solve for? I think h is easier, right? You take those w's to the other side and then divide by 2. So why don't we do that? Let's solve this for h. 2h equals 30 minus w minus 1/2 pi w. Divide by 2, h is 15 minus 1/2 w minus 1/4 pi w. So that's dividing every term by 2. And now I'll go back to my objective function. My objective function was area was equal to HW plus, what was it, 1/8 pi W squared. Was that what it was? Yeah. And all I'm going to do now is replace H with 15 minus 1/2 W minus 1/4 pi W. So the area now should all be in terms of W. So I'm going to write A of W. H, which is 15 minus 1/2 W minus 1/4 pi W. All of that times W plus 1/8 pi W squared. Distribute that W through. 15W minus 1/2 W squared minus 1/4 pi W squared plus 1/8 pi W squared. You can collect some like terms together here, right? These two. I mean, in fact, you could actually put the negative 1/2 W squared together with those, but let's just do those two. What would that turn out to be? What's 1/4 pi W squared plus 1/8 pi W squared? Negative 1/8, okay? So A of W equals 15W minus 1/2 W squared minus 1/8 pi W squared. And I'm pretty happy with that as being my final function that I'm going to do calculus on. So what do I need to consider now? What do I need to look at? What now? Domain. So what's my domain? Is there a restriction on which variable am I looking at? When I talk about domain, what variable am I looking at here? W, because that's the variable in the function, right? So is there a restriction on W? I'm going to go back up and take a look at my picture. What is the widest W can be? Can it be infinite? Can it be 50? Why not? Yeah, because the perimeter of the window has to be 30, right? The perimeter has to be 30. So there's no way you could let it be 50. Right? Because then one side of your window is longer than you're allowed to have the total window be. So there is a maximum, isn't there? And is there a minimum? Is there a smallest value that W can be? 0. 0, right? 0. So I agree that 0 is the max. I mean the minimum value it can be. So it's going to look like our domain will be something like, okay, 0 must be less than or equal to W, less than or equal to. Here's the question though, what's the biggest it can be? Well, we have to be careful because if we say 30, then isn't the top part of the circle 1/8 pi w squared? Yeah, so what we really need to find the domain is this. We would have to say that this part on top, the blue part on top, and this blue part on the bottom together would be 30. And then let h be 0. So I would have to solve this equation. I want w plus 1/8 pi w squared to be equal to 30, right? That's what I would need. What type of equation is that? Quadratic. You could solve it using quadratic formula, right? And you could get an answer. I'm going to skip that because what I'm going to do is just say, hey, look, I know it can't be bigger than 30, okay? I know it can't be, so I'm going to use that as my max. But if you really wanted to find the exact domain, you would have to go up here and solve that equation. So what we have is a continuous function, right, on a closed interval. So what are we going to do? Derivative? Okay, derivative. A prime. What's A prime? 15 minus 1w, right? Minus 1/4 pi w. Everyone agree with that? What do you do with that? Set it to 0 and figure out where it's undefined. So where's A prime 0? Where's A prime undefined? Well, it's never undefined because it's a linear function. It's 0 whenever I set it equal to 0. So let me do that. Oh, I'm out of room. Okay, I need to start a new page. Everyone have that? Here we go. 15 minus w minus 1/4 pi w equals 0. What I think I'll do is I'll take the two w terms to the other side to make them both positive. I'll factor out a w from both. And I'll divide through by this 1 plus 1/4 pi. Does everyone follow that and agree with that? Now, just for our own kind of understanding of what that number is, let's get our calculators and just get a decimal approximation to that so we have some better understanding of what that is as a number. I'm getting 8.4, approximately. Wait, 8.4 is approximately W. Is that within our domain? Yes? Okay, now this is a really important concept point here that I don't want people to miss. Because last class we ran into this question, and I never really answered it thoroughly enough in class. The question was, can't we always use the closed interval method? I mean, just find out where the derivative is 0, plug those in and compare them. What is the trouble with the closed interval method right now? With this problem, what's the trouble with it? Does anyone recognize what's wrong with our closed interval method? Look at our closed interval, 0 to 30, right? Didn't we guess at 30? Didn't I say in order to figure out what the actual end of the interval would be you would have to solve this equation, right? Doesn't the closed interval method require that I plug in the two endpoints and the critical number? And if I'm guessing at one of the endpoints, I'm not going to really know if I've got the minimum or maximum or not, right? So let me go back to this, and I want you to consider the following. Let's say that we were never given an interval, okay? Let's say this was an open interval. What would be the next step if this was an open interval? You would draw a number line, okay? You would plot, ooh, wow, that's really not straight. You would plot your point, right? Which would be 8.4. You would pick a point to the left and to the right and plug them into what? Derivative. So how about I take 1 and how about I take 10? What's a prime of 1? What's a prime of 10? So I go back to my derivative, which isn't even on this page. What would you get if you plugged 1 in, and what would you get if you plugged in 10? So I've got to go back to the derivative, which is right here. Plug 1 into that. 15 minus 1 minus 1/4 pi. That's still a positive number, isn't it? Yes? 13. So it's positive, right? Now plug in 10. If you plug in 10, you'll get negative. Yes? What that tells me back here is that my function, my area function goes up and then it goes down, which means that 8.4 is a local maximum, right? But why can I be assured that that's the only maximum? How can I be sure that the endpoints aren't higher? How do I know the endpoints of this function are not higher than that maximum? Well, but look at it though. Your function goes up then down. How could any point over here be higher or over here be higher? Wouldn't the function have to come back up? Right? Wouldn't it? This is the only place that the function goes up and then comes back down, right? At 8.4. Nowhere else on the function does it go back up. So it can't go back up to a higher point. Does this make sense or not? It's like you have a hump in your graph here. Yeah, now if you had additional critical numbers, you wouldn't be able to do it. Okay? If you had another one over here and it turned back up and then maybe another one turned back down, then you would have to compare the two and see which one gave you a bigger value. So I guess what I'm getting at is this. In order for you to truly have done the closed interval method, you would have had to have solved that quadratic equation that I showed you earlier to find what your endpoint had to be, and then use the closed interval method. But if not, if you want to avoid that, you could have used the open interval method and convinced yourself this is the only place you have a maximum by looking at this. Do I make sense or not here? No questions? So we have a maximum area when W equals approximately, or W is approximately 8.4, what, feet? And it wants the dimensions of the window, doesn't it? So what was the height? You have to go back to your formula for height. I think I remember, wasn't it like 1/2 W? I may be wrong here, going off memory. Whoa. Was that it? Okay. So plug in 8.4. I'm getting something like 4.2. feet. Is that all the information I need to know? Can you construct the Norman window off of just this information? Well, I don't think it asks for area, does it? It says find the dimensions of the window that will give the greatest possible amount of light emitted. So it just wants the dimensions. Yeah, see, that's all I need. This needs to be 8.4 feet. This needs to be 4.2 feet. And then the circle, remember, is just half a half circle like that. That's fixed, right? Because the 8.4 is the diameter. Well, if you can't figure out what the closed interval is, then you can treat it like an open interval, and then look for local max within what's reasonable, right? Like between 0 and 30, we know that if it only goes up and then down between 0 and 30, that's the only place I'm going to have a maximum, right? But let's say it went up, down, up, down, up, down 4 times between 0 and 20. I wouldn't be real sure about which one would give me the max. I'd still have to compare them. This is a great problem that was asked. I know for a fact that I've actually given that problem on a final before. What was the area function? Before we took the derivative, what was the area function? Wait, hold on. W squared. Oh, I'm using W. I need X. Hold on. Minus 0.5 W squared. Keep going. What I'm doing is I'm graphing this is the area function. There it is. There it is, like this. Okay? That's the area. If you let W be 0, of course you're going to have 0 area. Over here, somewhere, remember I said you'd have to solve the quadratic equation to figure out where that is. It's just the x-intercept of a parabola. And then somewhere in the middle is our, what's that? Well, yeah, you could, as long as it was right. For this, you could. This one, you can just do the zeros. Let's see, it's 0. Just so we know, it's 16.8. That's where, that would have been the closed interval, would have been from 0 to 16.8. And let me just verify that we got the max. So extreme values right there, 8.4, right? 8.4. And the maximum area, which it never asked for, would be 63.01 square feet. I mean, I hope that when you step back and you think about, what calculus is about here, what we've really done in this problem is we've found the maximum of a parabola. Okay? Which you could actually do the maximum of a parabola in college algebra. It's the vertex. But in calculus, if it was a cubic function or a sine function, you can find maximums and minimums. And now what we've done is we've tied them to word problems. Okay, good question. Anything else we want to talk about as far as the homework? 4.6. 4.6, number 13. Yes? Okay. Yeah, like what's your initial guess? Is that what you're saying? All right, so this is finding the roots of x to the fourth minus 2x cubed plus 5x squared minus 6 equals 0 in the interval 1, 2. Okay. It says use Newton's method to approximate the indicated root of the equation correct to 6 decimal places. So remember, what this is doing is it's taking a graph, you pick a point, it goes up to the point on the graph, draws a tangent, comes back down to the x-axis. Do you remember the visual of this or not? Where the tangent crosses the x, go up again, comes back. That's right. And you just repeat that until you keep getting closer to the true x-intercept. So this equation has an answer between 1 and 2. How do we know that it has an answer between 1 and 2? I mean, how do I know that? Plug in 1. What do you get if you plug 1 in right now? 1 minus 2 plus... Why does my freaking computer keep doing that? Plus 5 minus 6, which is what? Negative 2? Is that right? Okay. Now plug in 2. What's 2 to the 4th power? 16 minus, let's see, 2 cubed is 8 times 2. So minus 16 again. Plus, let's see, 2 squared 420. And then minus 6. This is 14. So how do I know that I have a solution to that equation between 1 and 2? Drum roll. How do I know between 1 and 2 this graph, this equation has a solution? There you go, Elias. That's it. Because at 1, if I were to look at the left side of this as a function, right? If I treat this as a function, then if I plug in 1, I get negative 2. And if I plug in 2, I get 14. So my graph must go from the blue, connect the blue points. And it has to be continuous, right? Meaning I can't pick up my pencil. Why? Is that a continuous function? X to the 4th minus 2x cubed plus... Yes, it's a polynomial, right? So I've got to connect these without picking up my pencil. So I have to go through 0, don't I? So there's somewhere in there that I pass through 0. I can't tell you where it is. But using Newton's method, we can approximate it. We can get real close. Okay, so Elias's question was, what point do you pick? And I say pick one of the endpoints. Let's try 2. So that means I'm going to let my x0, my x0, be 2. Now, what was the formula for Newton's method? X sub n plus 1 equals x sub n minus f of x sub n over f prime x sub n, right? Isn't that what it was? That means that if I try and get my next point, x sub 1, it will be x sub 0 minus f of x sub 0 over f prime x sub 0. So I would like to find the derivative before I continue doing anything else. If my original function is x to the 4th minus 2x cubed plus 5x squared minus 6, then the derivative of this is 4x cubed minus 6x squared plus 10x, and that's it. So we get to plug in, we're going to plug in 2 to start, right? So I'm continuing here, right here, I'm continuing with this, plugging in 2. So 2 minus f of 2 over f prime of 2, which is 2 minus, now f of 2, didn't we do that a second ago? It was 14. over, now plug 2 into the derivative. 2 cubed is 8, 32. 32 minus 24 plus 20, 28. Hey, isn't that exactly 2.5? Oh, wait, not 2.5, 1.5. Agreed? That's exactly 1.5. So that's x sub 1. Now, what's x sub 2? It's x sub 1 minus f of x sub 1 over f prime x sub 1, which is 1.5 minus f of 1.5 over f prime of 1.5. This is just tedious now, right? But as far as difficulty level, would you agree it's not so bad? I mean, it's just plug and chug. Elias, have I addressed your question?
Yeah.
Like, where do you start, right? Okay. They always gave you that initial, yeah. And you know what? When you ask a calculator to solve something like this, it just does a guess. It just starts somewhere. It just guesses. And then if it doesn't converge within a few tries, it tries something else. All right, I want to see what this turns out to be. So let me, it's 1.5 minus, hold on. I'm waiting for my calculator to do something here. Come on, man. F3. So I'm getting on the top, bless you, negative 18.9375 over 15. Is that right? Oh, no, it's not. I typed something in wrong. My apologies. The numerator, I think, is wrong. I'm not going to go through another step of this. This is the last step I'm going to do. Every time you do another iteration of this, your number should get closer and closer to something. It shouldn't be jumping all over the place. So let's see. If I plug in 1.5 into the original function, I get 3.5625. Anyone else get that? Okay. And did you get 15 into the derivative? Yeah. So what did you get for the answer? 1.26 for everything? Okay. And then you go again. And what the book is saying is that do it until you're correct to 6 decimal places. What would that mean? 6 decimal places. You keep going until I'm just going to make this up, but maybe the next time we do this, it's 1.2, what? Is that what it is? Oh, no. It won't necessarily do that every time, though. That's not the way it converges because it's not a linear type relationship. So let's say the next one you get 1.6254. Then the next time 1.26231. The next time 1.26204. You know what I'm saying? Like 1.26230. Let's say this was 47. 43. No. At some point, they want it correct to 6 decimal places, right? So they want the 6th decimal place. 1, 2, 3, 4, 5, 6. You see in the next line, those 6 didn't change, that's when you can stop. That's a tolerance, right? So the further you go, the more times you keep doing this, you can get it correct to more and more decimal places. So the Newton's method allows you to be as accurate as you want to be. And that's, like I said, that's what your computer does. It says, okay, once I keep doing this, and in the 15th decimal place, it stops changing, I'll stop. And I'll send that answer to the user. I'm not going to ask you for this many iterations on the test. Yeah, I'll just say when you're correct to like 2 decimal places, 3 decimal places. Yeah, it's not going to be like repeat 8 times, 10 times. You don't remember what how you started at 1.5? So you just picked a point. Oh, I don't know. I just picked an endpoint. Yep, I picked 2. Yep, yeah. And that was Eliza's initial question. It's like, what do you start with? I picked 2. You could have been 1.5, or you could have picked 1. Yep. That's right. What you don't want happening is this, though. Let's say our first time through we got 1.5, and the next time we got 2.3. And the next time we got negative 2.7. Then the next time 4.2. When you start getting that, there's issues. Because Newton's method will converge to an answer if your initial picking of your point is good enough. But we don't talk about what that is. We don't really get into that. Because you can you can take a function like, let me see. A good example might be something that's like a sine function like this. And maybe you're trying to find this x-intercept right here. So what you do is you pick an initial point over here, right? So that tangent sends you down here. That gives you this point. You go to the function here, and now that tangent sends you back over here. You go over here like this. That sends you back. That sends you back over here, right? Then you pick this point, and now it's going to give you a tangent that's going to send you over here. You see how those tangents keep sending me all over the frickin' place? Right? So it's not a perfect method unless your first guess is good enough.
Well, you didn't specify.
That's right, I didn't. That's why the book does. Because they know if you pick anything between 1 and 2, it's going to converge. Just sometimes it might take a little longer than others. See, like if I cut this off, let's say I were to take this same picture and I just cut off in here and I force you to pick a point in here. Now if I pick this, it's going to go and hit here, right? Then I go there, it's going to hit somewhere in here and then back up and then back down and back in, and it's going to start smashing into the 0. I hope that makes sense. Okay. All righty. That won't happen. I won't give you that. It's always going to give you, what's that? But it says start by drawing a graph to find initial approximations. So what they would want you to do is like go to a graphing calculator and graph the function and then say, it looks like it's close to 3. So I'll pick 3.5 or something like that. But they don't want you just randomly, just out of the blue, grab a point. All right. I'm gonna talk about 4.7 and chapter 5 a little bit. Today is not going to be this is not going to be real structured because we're kind of at the end of the course. This is kind of where we start to transition into Cal 2. All right. So I want to do a real quick kind of recap of what Cal 1 has been about, right? What did we start Cal 1 with? Can you nudge him real quick? Are you all right? Okay. Yeah, I know it's the last day, but I still don't like sleeping in my class. So, well, I would like to sleep in my class, but I don't like it if you're sleeping in my class. Half the time, I am sleeping up here and just like robotic talking. So where do we start Cal 1? Anyone remember what the whole class started with? Well, I mean, the first calculus topic, limits, right? From the idea of the limit came the idea of the derivative, right? And the derivative basically gave us the slope of the tangent line, right? And if we look at the derivative in terms of distance versus time, then the derivative was the instantaneous what? Instant velocity or speed. Okay? So if you tell me where something is at every point in time, I can tell you how fast it's going at every point in time, right? Anybody remember what the second derivative represented? Your instantaneous acceleration. Okay, so we had the idea of the derivative. Then we did implicit differentiation. When did we use implicit differentiation? Anyone recall? There's two variables, and we couldn't solve for one of them. Like something like this. Sine x plus y equals y squared x. And we were trying to find y prime, right? You can't get y by itself on one side of the equation, so you couldn't do a traditional derivative. So we introduced what's called implicit differentiation, right? And then we did, from that, related rates. Those are the word problems, right? A sphere is growing so that its volume is always increasing at a rate of blah, 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 blah. How fast is its diameter increasing when its volume is blah, blah, blah? So related rates, word problems. Then we got into, pretty much after that, we got into like graphs and then being able to do like max-min stuff. And then optimization. So if you look at this kind of as chunks, the limit and the derivative kind of went together, right? The limit is kind of the womb, right? And the derivative is the offspring of the limit. I like that analogy, right? You like that analogy? The limit birthed the derivative for us. So they are intimately connected to each other. And then we talk about velocity and acceleration from that. Then implicit differentiation gave us ways of differentiating equations that involved variables we couldn't solve for. And from that, we also could do related rates. Things like, what's the derivative of 1/3 pi r squared h? Something like that, right? We could say dv dt equals 1/3 pi, 2 dr dt. You remember all that stuff? I mean, so that required implicit differentiation. And then the graphs, finding max and mins, allowed us to do optimization. Like the problem we just did, the Norman window. So those are kind of like three basic chunks of Cal 1, right? Calculus 2 is a different ballgame, okay? Calculus 2 starts basically with the concept of the antiderivative. The antiderivative. And from that, okay, so that's the womb in Cal 2, is the antiderivative. From that, you have all these different things that come off of it, all right? The first thing is that if you're given acceleration versus time, you can recover from it velocity and position. So it's kind of like in Cal 1, if we were given the position of an object at every point in time, we could tell you the speed and the acceleration at every point in time, right? In Cal 2, we can actually go backwards. You start with the acceleration, you can go back to the speed and to the position. So anti meaning backwards, really. And then also, we get from the antiderivative this concept of area. And this is one of the huge things in Cal 2. What we do is we look at a graph, bless you, and we cut the graph off at 2 points. And we ask ourselves, what's the area underneath this? And it turns out that the area is connected to the antiderivative. So in Cal 2, you're able to find the area of very complicated shapes that don't have rectangles in them, right? Everyone can find the area of a rectangle, but find the area of that. It's hard to do, but Cal 2 you can. That kind of makes sense? And then you do something like this in Cal 2. You say, instead of looking at a single function, let's look at two functions like this. I'll do this one in black. Like that. So those are two polynomials. And they intersect each other at those 2 points, right? What's the area in between those two functions? Right? That seems like a reasonable question. You could look at that, where would this be applicable? I don't know, like taking a cross section of, that bottom one looks kind of, not like a real wing for an airplane, but think about a cross section of a wing of an airplane, right? Something like this. What's the area of a cross section of the wing of an airplane? You could figure that out using Cal 2. All right. Then you start to do some weird stuff in Cal 2. You do things like take this picture right here and imagine taking that and taking that picture that's on a piece of paper, bringing it out into three-dimensional space and just rotating it around the x-axis. So take that red thing in A right there with the question mark and flip it around the x-axis. If you flip it around the x-axis, you get something like this. Right, something like that, and there would be a solid. And what do you think the question in Cal 2 will be? What's the volume of that solid? Right? So you could take some pretty complicated looking things and find volumes of them. What would happen if I took that second one and wrapped it around the x-axis? You would get something like that again, right? What would the difference be, though? It's hollow inside, right? You would have something like this, but inside, both ends like that. You could put your finger through the middle of it, couldn't you? So it would obviously have a different volume than the one above it. Right? And hey, what stops us from rotating it? Why do we have to spin it around the x-axis? Why don't we go around the y-axis? So what would that top one look like wrapped around the y-axis? Wouldn't it be something like this? It's difficult to draw these right now for you. But if you wrap that top one around the y-axis, wouldn't you be able to put your finger through the middle of it? Isn't the volume of the two different completely? It's a completely different shape, isn't it? So these things that you do, these are called solids of revolution. And then you do something else in Cal 2. You take a function like this again, but instead of talking about areas, imagine taking that taking that graph, right? Taking those 2 points off the piece of paper, looking at it as a piece of string, and straightening it out and measuring how long it is. Right? If this were a rope, take it off the page, straighten it out, measure it. How long is it? That's called arc length. So you can do that in Cal 2. You can also revolve this around the x-axis and not only find the volume, you can find the surface area, which means if you were trying to paint the outside of it, you would know the area of that surface. All right? That's just the beginning of what Cal 2 is about. And then you get into sequences and series and polar coordinates and all these different things. But I want you to just see the beginning here, okay, of Cal 2, because that's what I want to talk about for the remainder of what I intend on doing today before we talk about the final. And that's to introduce you to the antiderivative. This is what some of the things you can do with it, all right? But what is it? What's the antiderivative? So here we go. Antiderivatives. This will be on the final. Capital F of x is called, I'm sorry? I'm not even going to label this as a section because I'm basically just teaching out of my head right now. I'm not teaching out of the book. This is just antiderivatives, what it's all about, kind of, okay? Capital F of x is called an antiderivative of little f of x if the following is true. The derivative of capital F of x equals little f of x. That's it. That's what an antiderivative is. It sounds simple, right? So let me give you some examples, all right? Example. Would you agree that capital F of x equals x to the fourth, x to the fourth is an antiderivative of little f of x equals 3x to the, 4x cubed. Is that true? Yes? Because according to this, to be an antiderivative means that if I take the derivative of this, right? Take the derivative of that. What is the derivative of that? 4x cubed. That is the other function over here, right? Well, what about this then? Capital F of x equals x to the fourth plus 2. Is that an antiderivative of this? It is also, isn't it? Because when I take derivative of x to the fourth plus 2, derivative of 2 is 0, and that still gives me 4x cubed. In fact, I can take x to the fourth minus 100 pi to the 70th power, right? 100 pi to the 70th power is a constant. When I take the derivative of that, I get 4x cubed. Right? So how many possible antiderivatives are there? Infinite. So there's an infinite number of antiderivatives, but they all look the same. They all have to look like what? all of them would have to look like capital F of x equals x to the fourth and a constant. Good. Plus some constant. It can't vary from that though, right? It's got to look like that. Now let me see if you can come up with one. Find an antiderivative of little f of x equals x to the fifth. Now be careful, because I'm not asking you for the derivative of x to the fifth, am I? If I was to say that, I'd say f prime of x. What's f prime of x? You would say 5x to the fourth. That's not what I'm saying, though. The antiderivative. So basically, I'm saying that is the derivative of something, right? What? You've got to, whatever function came from had to start with a power of 6, didn't it? Yes? 1/6. 1/6 x to the sixth. I'll talk about the c in a second. Do you see that? So I'm trying to cover up the 1/6. That's kind of weird. I can't cover it up. Imagine that 1/6 isn't there. What's derivative of x to the sixth? 6x to the fifth. So that would give me the x to the fifth, right? But I don't want that 6 in front. So I have to come in with the 1/6 in front of it to kill off the 6 when it comes down, right? Now I could have added any constant I want out here. So how about adding 0, which means don't add anything. That is an antiderivative, right? That's an antiderivative. Now if I were to ask you this instead, find the general antiderivative, then I would want it to look like this. Capital F of x equals 1/6 x to the sixth plus constant. Now that looks, every antiderivative of x to the fifth looks like that. Questions? New page. Find, let's say, antiderivative of f of x equals x to the n. So that's kind of like the x to the fifth a second ago, isn't it? What do we know about the antiderivative's power? What about the power? It's one more than that, right? So it's n plus 1. That way, when I take the derivative, that power comes down by 1 and becomes an n, right? But how are you going to get rid of the power that's in front? You know what I'm saying? Like the 6, we had to get rid of the sixth by dividing by 6. So what do we put in front of this then? 1 over n plus 1. Good. So if I say take the derivative of that, what you do is you'd bring the n plus 1 out front, right? Which would cancel with the n plus 1. And then you'd reduce the power by 1 and you would get n. Now if we wanted to make this the general antiderivative, we could say plus c, right? Agreed? This is known as the power rule for antiderivatives. Remember, we had the power rule for differentiation, right? Do you remember the power rule when we take derivatives? What's the derivative of x to the n? Nx to the n minus 1. Remember that? Now, this is the rule for going backwards. If you start with an x to the n, and you want to go backwards, you have to do 1 over n plus 1 times x to the n plus 1. Does anybody see a potential problem with this. There is a potential issue here. Go ahead. What's that? Yeah, well, yes. What about, what would cause this thing to not work? What power, what n would make this capital F of x be all messed up? If n was negative 1, right? What if n was negative 1? Then you would have 1 over 0, right, in your formula? So what we have to put on the end of this is if n is not equal to negative 1. So let me look at the case that it is. If n is equal to negative 1, then isn't my original function x to the negative 1? Right? The little f, isn't it x to the negative 1? Isn't that 1 over x? And what is it that we take the derivative of to get 1 over x? The natural log. Right? The derivative of natural log of x is 1 over x. So in the case that n is negative 1, the capital F of x will be equal to natural log of x plus c. So now we've covered it. If n is any number other than negative 1, we use the top one. If n is negative 1, the antiderivative is natural log of x. Okay. Y'all all right with this? We're going to try another example with that in mind. Find the general antiderivative of little f of x equals 1/2 x squared minus 3x to the 7th plus 2 square root of x minus the cube root of x plus 1 over x squared. Let's first write it down, but then let's appreciate that if I was asking you to take the derivative, which is I'm not, right? Could you do this derivative? You would get every power of x, right? You would get all the things in terms of power of x's, and then you would just do derivative power rule on each one, wouldn't you? And you would differentiate term by term, one at a time. No product rule, no power rule, right? No quotient rule, no chain rule here, right? Very, very straightforward. Well, to do antiderivatives, we're going to do the exact same thing. We're going to do antiderivative each one separately. And remember that when we had constants in front, we just leave them when we take derivatives? Same thing applies when you do antiderivatives. So here's what I'm going to do. I'm going to rewrite this function as 1/2 times x to the 2nd minus 3 times x to the 7th plus 2 times x to the 1/2 minus x to the 1/3 plus x to what power? X to the negative 2, right? Now I'm going to highlight where I have constants in front of functions, right? We're almost looking at this like there's a 1 there and a 1 there, right? So those are all my constants sitting in front of my powers. So let's just focus right now on x squared. What's the antiderivative of x squared? Use the formula that we just got. Careful. Remember the formula is 1 over n plus 1 x to the n plus 1, right? So n for us for x squared is 2, right? So 1/3 x cubed, right? 1/3 x cubed. 1/3 x cubed. All right, let's now look at this one right here. What's the antiderivative of x to the 7th? 1 what? 1/8 x to the 8th. All right, now be careful with this one. What's the antiderivative of x to the 1/2? What's 1/2 plus 1? 3/2, right? 1.5 or 3/2. So isn't this 1/3/2 x to the 3/2? Isn't it? That's 1/n plus 1 x to the n plus 1. What's this one? What's 1/3 plus 1? 4/3? 1/3 plus 1 is 4/3? Yes. It is. Yeah, no one. Thank you. You're probably sitting there going, what the hell? What's 1/3 plus 1? 4/3? So this is 1/4 x to the 4/3. Is that all right? How about this last one? What's -2 plus 1? -1. So we get 1/-1 x to the -1. Now I'm just going to throw all the numbers in front of these. 1/2, and then I have -3, then I have +2, then I had -1, and then +1. Now, I mean, you get to a point eventually where you can just do all this in your head because you've done it so many times, all right? But just starting out, I'm trying to show as much detail as possible. Let's look at that first one. 1/2 times 1/3 is 1/6. So I've got 1/6 x cubed minus, let's see, 3/8 x to the 8th. What is 1/3/2? It's 2/3, isn't it? It's the reciprocal. So this right here is really 2 times 2/3, which is 4/3. So plus 4/3 x to the 3/2 minus, again, 1/4 is 3/4. So 3/4 x to the 4/3. And then plus, and then -1, so minus 1/x. Where did 1/x come from? Nope, not. Careful. What is x to the -1? It's 1/x, right? Drop it down. Now I'm missing one thing here. I need to call this capital F of x, right? And if it's the general antiderivative, then I need what at the end? Plus c. So that's a good example of a power rule problem for finding antiderivatives. Now, there's some, do everyone have that? I'm going to move on. There's some other functions everyone should just know the antiderivatives of. Like, what's the antiderivative? Find the antiderivative of f of x equals cosine x. So what do you take the derivative of to get cosine? Careful. Is that right? Sure. Take the derivative of capital F. Wouldn't you get negative cosine? So it's just sine. right? The antiderivative of cosine is sine. What about this one? What's the antiderivative of sine? That's negative cosine. Because try it. Take the derivative of cosine x, it's negative sine x. Then make it negative, that'll give you positive. What are some other ones you would know? Should know. What's the antiderivative of secant squared x? Yeah. Just tangent. Just tangent. Right? Because derivative of tangent of x is secant squared x. Now, if you refer to your formula sheets that you're allowed to print on the test, right? Who has those with them? I want to refer. Can I borrow yours real quick so I can tell everyone what page it's on, whoever has it? You may not have all of them. You got them all stapled here? All right, so if you look at reference page 6, it has all of these. Now, I still need to show you what this notation means, but just for right now, just know that reference table 6 is where all these things are going to be. Yep. As I need to introduce that before I can refer you to that. I forgot about that. All right. Now, that's as far as we're going to go right now with the antiderivatives, just with this. Now I'm going to try and introduce you to something, a kind of a different concept. Riemann sum. I don't know if that's R-E-I or R-I-E. I forget. Riemann sums. All right. How many of you have ever seen this symbol before? Sigma. That's a Greek, that's the capital Greek S, right? Capital Greek S. Now, does anybody know what it stands for or represents in mathematics? A sum. Okay? That's the symbol for a sum. How many of you knew that? So, just show of hands. You knew that was a symbol for sum. Okay. That, whenever you see that symbol, it means you need to add things up. Okay? Technically, the way I do it is something like this. I'm just going to make something up. K squared plus 1. And I'm going to put what's called an index here. K equals 1 to 3. So the way it would work is this. You start at 1. Okay, the bottom of that sum, K equals 1. I start at 1. I plug 1 into that expression. What's 1 squared plus 1? 2. Then I add to that. Now I let K be 2. So I increase the number by 1 integer. So K goes 2. Now plug 2 in. What's 2 squared plus 1? 5. Plus 3 squared plus 1, 10, right? You add those up, you get what, 17? So this sum right here gives you this number, right? Got the basic idea? Now, you can have a sum that's finite, like this, or you can have a sum where you start at maybe 1 and you go infinite, which means you add things up forever. And here I'll give you an example of something you could add up forever. How about 1/2 to the K? 1/2 to the K. So let's start at 1. What would you get? 1/2 to the first power. Plus, now let K be 2. 1/4. Now let K be 3. 1 eighth, 1/16th, plus forever and ever, right? This would keep going. Here's just a question to you. If you add things up forever, is it always going to be unbounded? In other words, like if I were to take, let me put one right below this. K equals 1 to infinity of k. That would be 1, then I add to it, let k be 2, 2, let k be 3, 3, k be 4, 4, and I keep doing that forever. Let's label these A and B. They're both infinite sums, aren't they? Which one of those obviously is unbounded, like just becomes infinitely large? The second one, B, right? 1 plus 2 plus 3 plus 4 forever is going to just go to infinity, right? Bless you. What about the first one though? What about A? Will A actually keep getting bigger as I keep adding? Or is it bounded? Is there a limit to what that adds up to be? Each one of the pieces is close to 0, but it's never 0, right? This is a big, like, theoretical kind of question. Look at A. This is a very important thing. Cal 2, this is what you talk about, this part of what's called sequences and series. Right there, part A is called an infinite series, or a series. And what you do in Cal 2 is you actually figure out if that adds up to something or not. In this case, I'm just trying to ask you the general question. Do you think that adds up to something or not? Yes? Do you think it keeps getting bigger, or do you think that there's a cap, like it doesn't get past a certain number? Each one of those, you think it's approaching 1, but it never gets there? That seems to be...
Sequence is going to 0 that never gets there. If you add them all together, it approaches 1 that never...
Yeah, you can do it with like a cup, right? Imagine you have a cup, and the first thing you add to it is you fill it halfway, right? And then the next thing you do is you add 1/4 of a cup to it, right? So now that puts you up here. So there you've got your 1/2 with your 1/4 on top of it. Now you add 1/8, which is half of that, which puts you up here now, right? Then you add 1/16, which is half of that. And you keep doing that forever, don't you? You'll never overfill this cup. Which is really kind of a troubling thought sometimes, because what you're saying is that each one of these individually is a positive number, right? Guaranteed, each one of those numbers is positive. They are all bigger than 0. Yes? So you're telling me that if I take a positive number and add it to another positive number, and I keep doing that forever, that it's not going to become overfilling at some time? And the answer is yes, it will not. In some cases it overfills, in some cases it doesn't. So you study that in calculus too. It's called convergence or divergence. A here converges, B here diverges. Now, I'm getting a little sidetracked because what I'm trying to get you to look at right now is this stupid symbol, sigma, okay? Because the symbol is what's important here. All right, so now here's where I'm going to try and bring the symbol back to earth here. We have a function. Imagine we have a function, and we take it from one endpoint to another, and we want to figure out what the area underneath that is, right? What's the area underneath that function? No idea, right? No idea. What's one way we could approximate it? And let's act like we actually have the function. Like, I'm making this up completely. Like if we had the function right there, and let's say this point was 1 and this one was 2. How could we approximate the area underneath there? What geometric objects are you comfortable finding areas of? Rectangles, right? Rectangles and squares. Rectangles are just as easy as squares, right? So how about this? How about a really, really bad estimate like that? One rectangle. That rectangle is obviously too much, isn't it? Oh, let me try something else. How about I cut that interval in half and do a rectangle that goes up here and then another one that would go here. Well, that gave me kind of the same thing, didn't it? Didn't it? What if I go more rectangles? And go to just where the rectangle hits. Can you kind of see that the more rectangles I do, the better my approximation is going to be? I'll have less error in it. Sorry, I thought I had this right here. Where's my Riemann? There it is. Well, I don't know why it's not opening up here. Give it a second. There it goes. All right, this is better. So let me drag this sucker down. Okay, so there, I'm trying to find the area underneath that blue curve, right? 4 rectangles. Look at the area right here, 6.76. So the actual area is 5.75. Don't ask me where that comes from right now. Okay? That's my estimated area with those 4 rectangles. Here's the true area. What happens if I get more rectangles? Look at the error. Look at how I'm getting closer, right, to the true area. The more rectangles I do, the better my approximation. Yes? So what would be the best approximation ever? What would actually allow me to get to the true area? How many rectangles would I need? Infinitely many. Right? Infinitely many. Which means I need a sum of an infinite number of rectangles. Don't I? Y'all kind of see that? But you run into a problem. If there's an infinite number of rectangles, how wide then is each rectangle? 0, right? So what you're doing is you're letting your rectangle's width go to 0. So this is a limit problem. You're letting something approach 0 and you're trying to add things up forever. But it's a limit. It's basically the limit as the number of rectangles goes to infinity. So Riemann was a mathematician who actually came up with formulas for these sums. And Riemann determined that, look, if you go and you cut up this interval, you pick the point on the right side, plug it in, right side, plug it in, right side, plug it in, right side, plug it in. It gives you the same answer. Well, right now, look at the area. It's 6.76. If I were to do the left sides instead, so that means I go up the left side of the rectangle, come over, left side over. This is too little, isn't it? But watch what happens as I let it go to infinity. It still converges to the right answer. And he said, all right, it doesn't matter. You don't have to go left or right. You can go right in the middle. And if you do that, as long as you go to infinity, you still get the same area. So there are ways to do these sums by hand, but it's super tedious. Well, no, you'll see it's even better than a computer. All right. All right. I'm going to take something like x squared minus 1. Let's do that one. Right there. Let me do less rectangles. Okay, there's x squared minus 1. All right. Let me get back to my notes here. There's my drawing. My drawing sucks, doesn't it, compared to that computer one? So if I were to sit here and I come back to this idea, right? And I were to say, look, I'm going to take a rectangle in here, some arbitrary rectangle. How tall is the rectangle? Like if I'm picking some point x here, how tall is it there? It's the y value, isn't it? But isn't that f of x? Yes? So what would the area of just that little rectangle be? It would be f of x times, now you can't say x because x is a single point, isn't it? So x by itself has no width. So how about just calling this little thing delta x? So like if I had my interval, here was 1 and here was 2, if I had cut it into two rectangles, each one would be 1 unit wide. If I cut it into 3 rectangles, each one would be 1/3. If I cut it into 4 rectangles, do you understand? So I'm going to call this the change in x. That's basically my width. So the area of this is equal to that. And how do I find the area of the whole damn thing? I add all those rectangles up forever, right? I draw an infinite number of rectangles and I add them up forever. And that process of taking the sum as k equals 1 to infinity of each rectangle times its width and letting the number of rectangles go to infinity. So you're not going to be tested on this formula or anything like that. I just want you to understand this. What this is, right here, that's the area of one rectangle, isn't it? I'm going to add them all up. How many of them am I going to have? How many rectangles am I going to have? N of them. But then what am I going to let happen to n? I'm going to let the number of rectangles go to infinity. If you do this, this gives you the true area. Okay? Now, here's the big eureka thing, kind of. This right here, we don't like to write that over and over and over, so we have a shorthand notation for it. It is this. Now, this right here is called the integral sign. This function right here is called your integrand. And this right here is called your differential. And the differential becomes very important later on. Right now, it's really just the width of the rectangle. Okay? That's where it comes from. That delta x, that dx comes from the delta x. This f of x comes from that. And this integral sign is basically all that crap right there. Now, the integral sign, you could almost look at it as an S that's been stretched, right? Like an S that's stretched out. That S is kind of like the sum, the sigma. Okay? It's an S that's stretched. So the integral sign actually comes from the idea of an infinite sum. The limit of an infinite sum. All right. Y'all okay with this? Now, I think now is where the whole big result of today comes into play. It turns out, by what's called the fundamental theorem of calculus, which I'm not going to prove in this class, okay, that we have some very, very nice relationships between that sum and the antiderivative, okay? There's some very, very nice relationships. First of all, the first thing I want you to know is that if we're given a function like this, little f, and we're trying to find the area from A to B. Okay, so if we're trying to find that area, we already know it's that limit n goes to infinity, infinite sum of all those rectangles, right? But the fundamental theorem of calculus says this. It says that that integral And now I'm going to add something to this notation. A and B on the top and bottom. Those are called your limits of your integral. That just tells you where you're starting and ending your function. That right there, if you want to know that, figure out and calculate that area exactly. It's equal to capital F of B minus capital F of A. What's capital F? An antiderivative. This is a huge theorem. Like I said, I'm not going to prove it. We're just going to use it. It's saying, it's really remarkable what it's saying. It's saying if you want to find the area under a curve between 2 points, all you have to do is what? Find the antiderivative and then plug in B into it. Subtract from that what you get when you plug in A. And you have the answer. It's pretty amazing. And then from that, we have this other thing that I want to write down. Because of the relationship between the derivative and antiderivative, do you remember how I kept on asking you before in those examples? I kept on saying, find the antiderivative of this function. Find the antiderivative of this function. Find the antiderivative of this function. Instead of writing that over and over, if you just write this right here, really, if you write the left side, then that's just asking you to find the antiderivative of a function. That's all that means. So we have two things here. An area, number one, has to do with areas, and number two is just like how to ask someone to find an antiderivative. So I think it's time to do some examples. All right? We're almost done. I know it's sad. Example. Find So what am I asking you for? Just find the antiderivative of that, right? That's all that means. This dx right here, don't get all freaked out by that. All that dx really does for you right now is just keeps track of your variable. Okay, your variable in the problem is x. So you're really trying to find the antiderivative of x to what power? -1/2. And using that rule we just used, right, 1 over n plus 1, x to the n plus 1, this should be equal to 1 over, what's n plus 1 here? -1/2 plus 1, which is 1/2. X to the 1/2 again, plus some constant, right? But that's really, 1 over 1/2 is really 2. And what's x to the 1/2? Square root of x, plus a constant. Does everyone see that this is just another way of me asking you this question? Find general antiderivative of f of x equals 1 over square root of x. Does everyone realize that what I highlighted in yellow there is basically me asking you the exact same questions down there, but without having to write all those words out? Yes? Okay. Just remember to add, always put your plus C. I'm not a huge like, oh man, you forget to add plus C and I'm going to count it all wrong. But I know that there are instructors that will count the entire problem wrong if you don't put the plus C. That C is called what's called the constant of integration. All right. So check this out. Next example. Find the area under f of x equals x on the interval 0, 2. So in terms of calculus, here's what I'm asking for. The integral, the way we say this, the integral from 0 to 2, what's the function I'm trying to find the antiderivative of? X dx. Now, according to the fundamental theorem of calculus, what I need is the antiderivative at b minus the antiderivative at a, right? That's what I need. I put it in red just to remind you of what you actually need to find now. What is the antiderivative of x? Antiderivative. It's 1 over 2 x squared. So I'm going to put a little side note over here. I'll do it in green. Capital F of x is 1 over 2x squared, right? That's the antiderivative. Any questions on where I got that? But don't I now have to plug 2 into it and then subtract from that what I get when I plug in 0? Yay or nay? Yes? Okay, now, because we do this a lot in calculus too, let me show you the way that we normally do it. What we do at this point, instead of writing down f of b minus f of a, capital F of b minus capital F of a, what we do is we write down the general antiderivative. Okay? Just like that. And then what we do is we put a line behind it, and we put 0 and 2. And what that allows me to do is not have to write it on the side like I did in green. I'm moving through this problem. I say, okay, what is this? Okay, well, I need the antiderivative. Here it is. And then I've got to plug 0 and 2 into it. But I actually plug in 2 first and subtract from it what I get when I plug in 0. So I'm going to write down here now 2 sets of parentheses. This first one will be capital F of B. The next one will be capital F of A. So plug 2 into that, and what do you get? You get 2, right? And plug in 0, and you get 0. Agreed? So the answer is 2. On top, yes. Yeah, I should probably label this over here. This is your B, this is your A. Or if you want, A and B are the endpoints of the interval, 0 and 2 up there. Now, I made this problem extremely easy because I wanted to be able to verify it with the picture. The function we had was the identity function, wasn't it? F of x equals x. And we were looking between where and where? 0 and 2. What's the value of the function at 2? If you plug in 2, you get out 2, don't you? And I wanted the area in here. But that's a rectangle. I mean, that's half a rectangle, isn't it? Or half a square. What's the area of the entire square here? 4, right? 2 by 2 square. But since it's the identity, it's diagonal, so it's half of that, so the answer is 2. I just wanted to show you that it works, right? And it's not a coincidence. It works all the time. Let's do another one. Do you want to break? You want to break before we do another one? Yeah, let's take a break. 10 minutes. We'll come back. It's just starting to get fun. All right, so look. What we have here is a wire. It's 10 meters long. You're going to cut it somewhere, right? So I'm going to cut it, let's say right here. And therefore the distance from here to here, we'll call it x. And therefore, the distance the rest of the way is 10 minus x. Does everyone see why that's true? So if we cut it 2 meters, we would have 8 left. Cut it 3, we'd have 7. Cut it x, it's 10 minus x. We take the first part, highlighted in yellow, we bend it into a square, and because we use the entire x to go all the way around that square, that means each side of the square is 1/4 x. 1/4 x. 1/4 x. Because we have 4 equal sides, don't we? Like that. Now the other part, we take it and we form it into a triangle, and it's an equilateral triangle. That means I took the 10 minus x and cut it into 3 equal pieces, right? So that gives me 10 minus x, 1/3 of that, 10 minus x, 1/3 of that, 10 minus x, 1/3 of that. So those are just the lengths of the sides. Agreed? Now we want to talk about the area, right? Because they want to know, where do I cut it so I get the most area, and where do I cut it so I get the least area when I add the two together? So I'm trying to look for total area of this added to this area. So the total area of both together is the area of the square plus the area of the triangle together. What is the area of a square? It's just the two sides multiplied together, right? So that's 1/4 x times 1/4 x again, right? So just 1/4 x squared. Any questions on that? We're okay? The triangle is the tricky one. How do you find the area of an equilateral triangle? Most people say, okay, if I could have the height, then I know the area of a triangle, but you're not given the height here. So the formula that I recommend you use is the one that I did refer to in class earlier this semester. It says that if you know two sides of a triangle and the angle between them, then the area of that is 1/2 AB sine theta. For us, do we know two sides of this triangle, the equilateral one? Do we know two sides? Sure. I've got this one. I've got this one. Do we know the angle between them? Because it's equilateral, right? All the angles are the same. This is 60 degrees in here. 60, 60, 60. Therefore, this formula becomes 1/2 AB sine of 60 degrees. So area is 1/2 AB sine of 60 is √3/2. So you get √3/4 AB is the area. Did you do it with the height? That what? So you found the height? So the √3/2, same thing, yeah. Okay, so any questions up to this? Now, A and B are the same, aren't they? In that formula, the blue formula there? It's 10 minus x over 3. So this will become plus, here's my area of my triangle. It's √3/4 times the 10 minus x over 3 times itself, so squared. So if I clean this up a little bit, area is all in terms of x, is 1/16 x squared plus √3/4 times 100 minus 20x plus x squared, all of this over 9. What did I do there? What did I do there? I just FOILed out, like the first one, 1/4 x times 1/4 x is 1/16 x squared, right? Everyone's okay with that becoming that? And then what I did is I took this right here and I squared it. Well, 10 minus x squared is 10 minus x times 10 minus x, which if you multiply it all out and collect like terms, you get 100 minus 20x plus x squared. And then you square the 3, you get 9. And then I can distribute the root 3 over 4 through the parentheses on the right to get 1/16 x squared plus, oh wow, okay, 100 root 3 over 36 minus 20 root 3 over 36x plus root 3 over 36x squared. So there I took the root 3 over 4. I distributed it to each of those, and then I divided each of those by 9. I'm doing all that because I'm trying to get it to something where it's going to be easy to take the derivative. I could have taken derivative before, but I'm cleaning it up a little bit. Is there a restriction on x? This is my area function. Is there a restriction on x? 0 to 10, right? The smallest I go is to not cut it at all and use the entire thing to make a triangle, right? Or I could cut it all the way at the end, which really means don't use any triangle and make it all a square. Does everyone understand that? If we let it be 0, we get all triangle. This means all square. So I have a continuous function closed interval. Take derivative. Let's see, 1/8 x, derivative of that's 0, minus 20 root 3 over 36 plus 2 root 3 over 36x. Now you can clean up that 20 root 3 over 36 and all that. Those are just decimals. Set this thing equal to 0. You should get, what'd you get over there? 4 point what? 34? And if I were doing this problem, I wouldn't even care about the closed interval. All I would do is set up a number line, 4.34, and I would just show that it went down then up, which would give me a minimum. And then to find the maximum, I would just plug the 2 endpoints into the original function. Or just use a closed interval method, whatever you're happier with. Okay, I don't want to take any more of the time. That problem's right out of the book. So, interesting problem. Let's get back to where we were. I'm going to give everyone 100 on that. How about, you like that? Is that okay? No complaints on that? Where were we? Where had I stopped? Okay, I remember what I was going to do next. So here's another example. Find area under y equals sine x on the interval 0, pi. So graphically speaking, here's our sine function, right? I'm trying to ask you to give me the area under one of these arcs right here of sine. Haven't you ever looked at the sine function and wondered what the area is under that? Yeah, no. That's why I asked. I don't think you ever have, but now, next time you look at sine, cosine, that's probably the first thing you're going to think. Wonder what the area is under that. Well, what is this as far as this integral thing and all that stuff I've been showing you? Integral sign, right? What do I put on the bottom? 0. What do I put on top? Pi. That means I'm going from 0 to pi. What function am I going to use for the integrand? Sine x and then dx, right? dx just keeps track of my variable, right? At this point in time, as you move into Cal 2, you'll see that plays a much bigger role. Just for now, it's keeping track of my variable. Now, what does that mean? That should tell you right there, find the antiderivative. So what's the antiderivative of sine? Negative cosine. Good. Negative cosine. Now, I put that little line at the end. I put 0 and pi here, don't I? That keeps track of everything. I'm going to take negative cosine x. I'm going to plug in pi. Then I'm going to plug in 0. So then you put equals. I always love to put 2 sets of parentheses. First one is what I get when I plug in pi. So negative cosine pi. The other one is what I get when I plug in 0. Negative cosine 0. Notice my negatives there, right? What is cosine pi? Negative 1. So I have negative 1. What is cosine 0? 1. So minus 1. So what is negative 1? 1. What's minus 1? Plus. So the answer is 2. The area under that is 2. That's right. Doesn't seem like it would be a nice number like that, right?
Pi is one of the weird numbers that makes everything better.
It is. Much like E. Now, I'm curious, what if I were to change this problem? Instead of making it go from 0 to pi, what if I were to come up here 0 to pi, and what if I were to change it to 2 pi? Do you think the answer would be 4? Well, all that would change would be, watch, I'm working with this integral, it would be 2 pi here, right? It would be 2 pi here. Do y'all see where I'm changing this? It would be 2 pi here. What's cosine of 2 pi? It'd be 1. So I'd have negative 1, but then plus 1, which would be 0. What does that mean? It's counting anything below the x-axis as negative. And it comes back to the idea of the rectangle. Do you remember when we said that when we take a rectangle in here, we said how high is it? And we said it's the function's value, right? F of x. But what if f of x is negative? Then it counts that little rectangle as having a negative area. Even though we know it's not negative area, it's a negative number times a positive number, which gives you a negative. So it counteracts the top side, and you get 0. So you have to be careful with things like that. So in a Cal 2 class, as you move on, you are not going to have this in this class. You would have to find out where the x-intercepts are. If they ask you, what's the total area under this curve? Then you would have to find the x-intercepts, break it up, and do them piece by piece. And so you would make two integrals, one going from 0 to pi, the other integral going from pi to 2 pi. When this answer over here, when this answer comes out to be negative 1, you would actually make it a positive I'm sorry, -2. You make it a positive. Okay, that's beyond the scope of this class. All right, let's talk about the final. Okay? Talk about the final. So let me pull out these finals here. Remember, there's going to be two finals, right? Two versions. Final version 1. Final version 2. Now, this is going to be 30% of your grade. That's what the final is, the way it is in the syllabus, right? 30% of your grade. That final, like I said, will cover implicit, related rates, sketch, optimization, integral. That's pretty much it.
As far as chapter 4 goes, that would be section like 4.4 to
4.4, yes. Well, max and min is kind of in the sketching, right? I mean, that's kind of why I don't need to go back and test it. And then when I get to optimization, I could give you a problem that it's on a closed interval, so you have to employ the closed interval method. So there's no need to give you like, okay, find the max of this function. It's built into the other problems. That's it for the 30% test. I can't imagine it would be more than probably for each of these, like one implicit problem, one related rate problem, one sketching problem, one optimization problem, maybe about 3 integral problems. Pardon me? Am I going to do what? I can't hear you. What? Oh, Newton. Y'all want Newton? Y'all want Newton, right? Newton's pretty easy, right? Yeah, Newton. How about we just do the whole final, just one Newton problem? Yeah, Newton's, that's really mechanical. That's why I leave it off usually. It's not in my head because it's not something that we normally test. But if you want it, I'll put it on there. It can probably help you out a little bit. Now, one thing I will say about the related rates problem, I'll probably, choose from 2. So I'll give you 2, you pick 1. Same with sketch, same with optimization. So that way I give you 2, and if for some reason it's just like you freak out when you see anything that has to do with the sphere, maybe the other one that has triangles in it will be better or something. I don't know, right? No, I know that you want that, but here's the deal. The way I see it is this. Whenever I give you 2 to choose from, it's to help you. It's to help you, right? So it's not to. I don't even know how to explain it. It's not designed for bonus. If that were the case, I would tell you do just this related rate, and then I'd offer a bonus separately. The fact that you have 2 problems to choose from is beneficial to you. Yeah, I mean that's the bonus, is the fact that you get to choose. Yeah. Yes. Okay, as far as weight, I would say I haven't really thought too much about this. 20, 40, 60. I'd probably say 20, 20, 20. That's 60% of the test right there. And the other 3 would be the rest. Probably more like 15 here, and then the rest of it here with these 2. How much is left? 5, 10, like that, something like that? Does that add up? 30? Where am I? I still need 10 points? Okay, so the highest you can score is a 90. No, I'm kidding. Yeah, I don't know. I mean, you're asking me a lot of detail here. I mean, that 60% of the test is right there. That's what I'll say. 60% of it's there. How the other part's going to break up, I'm not sure yet. But, you know, that implicit question, when I say implicit, you should be prepared to come in here and find the equation of a tangent line. I give you an equation that has x's and y's mixed up, and I say find the equation of the tangent line at this point. So that means you have to find the derivative, you have to, figure out the slope at that point, plug it all back in. Implicit doesn't just mean like find y prime. What's that? I don't know. I mean, rocket. Yeah. I'm not going to pull, a rabbit out on you and just like go crazy. I'll try and keep it, within reason. To me, when it comes to related rates, with basic problem, there's usually triangles. Things like spheres, things growing like that, circles. I mean, the easiest would be like rectangles and circles. And then you get to spheres. Related rates. I like the one with the cone, something being poured into. I like those problems. Sketching. I mean, those can get nasty, those problems right there. So I'll probably keep it pretty reasonable. Polynomial or rational function. Maybe a square root in there. I think one of your homeworks was a square root. So I haven't even talked about version 2 yet. Yeah. Well, if you take version 2, then what it does is this. Remember, the way that this class was broken up, it was 30% was quizzes, 20 was exam 1, 20 was exam 2, right? Oops. And then 30 was the final, right? Right? The way that I'll do it, if you do version 2, the final, instead of being 30, will be 40% of your grade. And what will happen is I will pick which exam is lower for you and make it only 10% as opposed to 20. Now, version 2 is going to be different because version 2 can include anything. It'll be this with material from exam 1 and exam 2 also. Yeah. So now, I mean, the weights are all different. Usually what I do is this. I mean, usually everyone gets the same test when you walk in. So everyone will get this. And then when the people who want to do version 2 finish that, they come up to me and I look at it. And if it's even worth it, we hand you the next version, the rest of the problems. Because if you did a certain level on this part, that may dictate whether or not it's worth the time for you to spend another hour and a half, 2 hours on the other stuff. It may not make a difference. So I'll look at it first. But the option is there. That part first, then the other part. Yep. That everyone has to do it that way.
So everyone's taking final one.
Everyone's taking version 1. Yep. And then handing it in, and people who were taking the option to, you're basically saying, I want this to count as 40%. Give me the extra problems now. Yeah. That kind of makes sense? Let's see, we've had one on each test, right? No, on the last one we did, right? Yeah, you can have a cheat sheet. I don't mind. You already have one from the last test, right? Okay. So you can reuse that one or make a whole new one. It's up to you. But still only one. And then, of course, all those formulas.
So is the quiz, ready to go? Are you gonna drop the quiz or?
Yes, I mean, remember the last test I curved 20 points. So I thought about dropping like 2 quizzes or something like that, or 3 quizzes, but because I curved the last test 20 points, and I just gave you another 100 on a quiz just now, I think it's probably just going to be one.
You're gonna drop one quiz,
Yeah.
pretty much figure out what our quiz,
Yeah, I mean, I don't mind updating all the quiz stuff right now, but you'll have to wait if you want to know. Is there anything in particular that you want me to start going over? I mean, I stopped class at the point I did because I wanted to be able to answer any questions about the final and talk about any topic off the final and not run out of time. So, is there anything that you have any concerns about, or something off of the? I know some of us, like you took the test and then you look back and you're like trying to figure out what you did wrong. Is there anything that you still are confused about that you want me to go over off of anything? If not, I have a couple of old tests here. I'm willing to talk a little bit about these. Sure. Yeah. One point. I have to make it one? No, I'm just kidding. I mean, the common things: related rates, optimization. I mean, it's the confidence that you have to get where you can get to the get through the problem. It's a process. I mean, all these problems: related rates, sketching, optimization. They're all processes, and there's little intricate details in each one. So I think a lot of you are mechanically okay. I mean, you can take derivatives and that stuff, but it's the higher level thinking is what I want to test on. Related rates. Okay, let me give you one. I don't even think we ever did a problem like this. We have a oh, by the way, if you feel like you're ready for the test and you want to take off, you can. I'm not going to hold you back. Just be aware that if you do leave and I say something to the rest of the class, like, I don't know, I'm not even saying I'm going to say anything. I'm just saying if for some reason I'm just sitting here, I go, oh yeah, one time I did this and la la la, and I wind up asking that on a bonus question, you don't know, you can watch the video of whatever you would miss in the next half hour. That's on you, okay? But you're free to go if you feel comfortable. You're not going to hurt my feelings. No, I'm saying right now. Like if you leave, I'm saying if you'd like to leave, you can. I'm going to go over some problems, but if you'd like to leave, you can. But if when you walk out, I tell everyone this deep secret about calculus that, you know, and then on the test you're like, what? I didn't know that. That would be on you. The secret. Okay, so you have a barn and you have a river. This barn is, let's say, 100 feet long. And you're going to try and build. Yep. This is looking from the top. You're going to build 3 identical, those don't look identical, but 3 identical enclosures for, let's say, some chickens, and then maybe some, I don't know, pigs, and then goats, and unicorns, whatever it is that you have. And I didn't do a problem like this, right? I didn't do anything like this. Let's say that here's the deal. You have the need to make each pen have an area of, let's say, 30 square feet. What do you think the question is? I was going to start talking like a farmer and start talking about, you know, this, but I don't want to stereotype any farmers. So I'm sitting out there, I'm looking out there going, I want each pen to have 30 square feet so my chickens and pigs and goats are happy. Okay? So what do you think? I mean, probably, I don't know if farmers really think like this. I would hope they do, but how do you, well, who can tell me what the question someone should ask themselves here would be? How much fence do I need? Yes, to do this. But a better question would be the least amount of fence I need, right? If I'm paying fence isn't cheap, right? Especially if I'm going to be putting in like a bunch of barbed wire fence for these chickens and pigs and goats, right? Or whatever it is, you know. It's going to be made out of like platinum or, you know, platinum chain link platinum fence. $300,000 a square foot or something. No. You know what I'm saying? It matters if I can minimize the cost, right? Yes.
It's just random, but like literally like in the area versus siding, the square has the most area for each side. Is the square better than a circle? Just like this, or the circle being the best area for the side? So a circle.
Okay, so you're saying for a fixed perimeter, what gives you more area, a circle or a square?
Yeah.
Is that what you're asking? Or are you saying,
Well, like the amount of area you get per how much fits you have. Set perimeter, what shape is your most area? Yeah.
okay,
The circle is
great question. You can answer that question. Not right now. I mean, you can't maybe think of it, but you can answer that question. How would you answer that question? I'll give you a minute to think about it. I don't want to put you on the spot, but think about it. You're asking a perfect question. If you have some geometric shape that has a fixed perimeter, let's say, what's the optimum shape to get the most area? Is that what you want? Yeah. If you want to compare a square and a circle, you could do that.
So,
Yeah. Well, it may not even be that difficult.
might not be optimization.
Yeah, I mean, just pick a number.
Figure it out. It's a circle.
Yeah, it'll be a circle. Yeah. I mean, have a generic perimeter of 1. Have a generic perimeter of 1, and then figure out from that what the areas of each each one would be. Make a square with perimeter of 1 and a circle perimeter of 1. Compute the areas of each one and compare them. So, okay. That reminds me, why are manhole covers circles? Y'all ever heard that one? You've heard that? Manhole covers are round because a circle won't fall into the hole. If you had a square manhole cover, if you turned it on its diagonal, it could fall down into the hole, but circles can't fall into holes. Just kind of random, useless information. Let's get back to the pigs and the goats. It is. And most of the pipes are round too, so it makes sense, but that's not usually it. Yeah. Mm-hmm. All right. Okay. So the answer, the question that the farmer should be asking is, how can I make this happen and spend the least amount of money? So I need to buy the least amount of fence, right? Now let's discuss some things here. Where does the farmer actually need fence? Right here, right here, right here, and right here. Technically, he won't need it along the river if we assume the chickens can't swim. I don't know if chickens can swim. That's true. Okay, well let's make these no, because there's still alligators in there. Why don't we just make this like a tiger so the alligators won't mess with them or something? The idea is just that we don't need fence along there, okay? Or if you don't want to make this too freaking confusing, let's just make this the other part of the barn. The barn makes like an L shape or something. Okay, so we don't need fence up against there. Okay? So what is it that we're trying to optimize? Okay, total length of fence, right? We want to optimize the length of fence. What is the length of the fence? And let's just call it L. How about that for length? What is the length of the fence? Oh yeah, optimize. What do we want? The most or the least? So we want actually to minimize this. So what is the length of that total length of the fence? I don't know, but I need to start assigning some variables, right? So farmer comes out here and says, okay, I can say that this distance from here to here, I could call that X, right? And I could take distance from here to here and I could call that Y. So what's the total length of fence used then? 3Y plus X. That's my objective equation, isn't it? But I need that in terms of one variable, not two. So there's some other constraint I need to put in place here. What's my constraint? Constraint. What's my constraint? The area must be 30, right? What is the area? I'm not sure. What did I say? Each pen has to have it. Thank you. Each pen has to have an area of 30. Thank you. 90, yes. Yeah, each pen has to have 30, so 30, 30, 30, 90. Okay. So that means the x times the y has to be equal to 90. Do y'all agree with that? Because of the way I drew it, x is the entire side, y is the length. So can't I solve that for either x or y? Yes? What do you want? I don't care. X or y? X? Okay. X is equal to 90 over y. So now we come back into our length equation. 3y plus x, but x is 90 over y. Now we're going to run into some issues. Do we have a restriction on y? What's the smallest y could be? 0? Could y be 0? Look at your length equation. Look at your length function. Can y be 0 in here? You divide by 0, right? So I know that y must be bigger than 0, can't be equal. Is there a maximum that y could be? Is there a maximum that it could be? I can make those pins as long as I want, right? The longer they get, the more narrow they get, right? But eventually, I'll reach some restriction. I'll either run out of the barn, right? The barn I'll come off the edge of the barn, in which case all the geometry changes. Or the goats and the pigs, like I can't put them in a 3-inch narrow pen, right? And have it be like 50 feet long. You know what I'm saying? Can't have that happen. So I don't really know what the restriction is on y. I'm going to concede that, which means I'm going to treat it like an open interval problem. Okay? And let's just find a derivative and see where it takes us. So what is the derivative? What is L prime? What's the derivative of 3y? 3. What's the derivative of 90 over y? Negative 90 over y squared. That's just by treating 90 over y as the same as 90y to the negative 1, then taking the derivative. Set that equal to 0. I'm going to move my 90 over y squared to the other side. I'm going to multiply both sides by y squared, divide by 3. Square root of 30. Okay. And I don't have to consider the negative one here, right? I'm going to do open interval method, so I'm going to just look at root 30, pick something to the left and to the right of it, and plug them into the derivative. I'm not going to actually do it, but it's going to go up then down. Oh no, other way. It's going to go down then up. Yep, 5 and 6 would work. And where are you plugging those into? Derivative. So that tells you have a local minimum at y equals the square root of 30, which means that's where you're going to have the least amount of fence. That's what you want. So what's x? 90 over y, right? 90 over root 30. So that's it. I wanted the dimensions or something, or I don't even know what I said. How do you build it, right? That's how you build it. You let your x be 90 over square root of 30, and the other side square root of 30. I'm looking at the time. It's 4:15. I'm just wondering if we even have time for anything else worthy of doing. Is there anything you want me to talk about or do? We're good? What I'll do is I'll hang out for the next 10, 15 minutes and I'm going to put in all the quiz grades, drop the lowest, and if you want to hang out, you can. Okay? Just to figure out where you are. Here's the thing, though. It's going to be hard for me to tell you, oh, if I do version 2, then what? I mean, that's going to be a little tough. I might be able to do it quickly, but we'll just see.